Chapter 2. Engine Cycles. The term cycle refers to one complete sequence of operations required to produce power in an engine. This cycle of operations is continuously repeated while the engine is running. For a diesel engine, it consists of 4 operations within the cylinder. The first is the compression of a charge of air. The second, the injection of fuel, which then ignites. The third, the expansion of the hot gases formed during combustion. And the fourth, the expulsion of the used gas to exhaust. The cylinder is then recharged with air and the cycle is repeated. Diesel engines can be designed to complete this cycle once during each revolution, and this is termed the 2-stroke cycle, or alternatively, to take 2 engine revolutions to complete, the 4-stroke cycle. An engine can only operate on the cycle for which it was designed. Engine stroke is measured as the full distance through which the piston moves between each end of its travel. It can be seen that it must move through 2 complete strokes, one up and one down, during each revolution of the engine. Engine timing refers to the relative time or position of the crank at which each operation during the cycle is commenced and is completed. It is measured as the angle through which the crank has been rotated from a datum position, such as top or bottom centre. The 2-stroke cycle. Practically all large slow-speed direct-drive marine diesel engines operate on the 2-stroke cycle, which is displayed on Figure 10, which is on page 15 of the book. Complete the 4-stroke cycle. An engine can only operate on the cycle for which it was designed. Engine stroke is measured as the full distance through which the piston moves between each end of its travel. It can be seen that it must move through 2 complete strokes, one up and one down, during each revolution of the engine. Engine timing refers to the relative time or position of the crank at which each operation during the cycle is commenced and is completed. It is measured as the angle through which the crank has been rotated from a datum position, such as top or bottom centre. The 2-stroke cycle. Practically all large slow-speed direct-drive marine diesel engines operate on the 2-stroke cycle, which is displayed on Figure 10, which is on page 15 of the book. The connecting rod length to the crank length, the ratio of the stroke to the bore, the engine speed and the engine rating, and so on. The 4-stroke cycle. The majority of medium and high-speed diesel engines for main or auxiliary drive operate on the 4-stroke cycle, which takes place during 4 consecutive strokes, or 2 complete revolutions, of the engine. The 4 strokes may be termed compression stroke, power or expansion stroke, exhaust stroke, and aspirating or air induction stroke. This is shown on Figure 11, which is on page 16 of the book. Indicator diagrams. An indicator diagram is a pressure against volume graph taken from the pressures in the cylinder of a working engine. It is plotted as a continuous line showing all pressure changes during one complete engine cycle. Indicator diagrams can be of great assistance to students in understanding the operation of an engine. Examination candidates are required to be familiar with the information which may be obtained from their shape and dimensions. In many modern engines, sophisticated measuring devices may be fitted to record cylinder pressures as an oscilloscope trace or printout. Usually these are not complete, closed indicator diagrams, and they are described later in this chapter. For some slow-speed engines, it is possible to obtain indicator diagrams from each cylinder by using an engine indicator. Engine indicator. Briefly, this consists of a spring-loaded piston on which the spring is compressed in proportion to the cylinder pressure acting on it. This is shown in Figure 12, which is on page 17 of the book. The piston moves a pen attached to an arm through a parallel link mechanism. A card with a sensitized surface is wrapped around the indicator drum. The indicator cock for the chosen cylinder is first blown through to clear it of carbon, and the indicator is then connected to it. The cord on the indicator drum is attached to some form of engine stroke synchronizing mechanism from the crosshead or cam. The cock is now opened and the indicator pen is held against the card, tracing a diagram for one cycle of the engine. Pressure is recorded to a vertical scale according to the stiffness of the indicator compression spring. Corresponding cylinder swept volume is recorded on a horizontal scale due to rotation of the drum by its cord. By turning the indicator cock to a vent position, a horizontal line representing atmospheric pressure is added to the diagram. This can act as a pressure datum line. 4 types of indicator diagram can be obtained. These are illustrated for a 2-stroke engine. Power card is taken with the indicator drum in phase with the piston movement. This is shown in figure 13, also on page 17 of the book. The area within this diagram represents the work done during the cycle to scale. This may be used to calculate the power produced or the mean indicated pressure, MIP, for the cylinder. Irregularities in the shape of the diagram will show operational faults. Maximum or peak pressure may be measured to scale between the atmospheric line and the highest point on the diagram. Power cards for 2 and 4-stroke cycles are shown in figures 10 and 11, drawn vertically to relate to the corresponding timing diagrams. It can be seen that in the 4-stroke cycle, pressure changes are so low during the last 2 strokes that these appear as straight lines. Compression diagrams, shown in figure 14 on page 18 of the book. Taken in a similar manner to the power cards, but with the fuel shut off from the cylinder. The height of this curve shows maximum compression pressure. If compression and expansion lines coincide, it shows that the indicator is correctly synchronized with the engine. Reduction in height of this diagram shows low compression, which may be due to a worn cylinder liner, faulty piston rings, insufficient scavenge air, or a leaky exhaust valve, any of which will cause poor combustion. Draw card or out of phase diagram, shown in figure 15, also on page 18. Taken in a similar manner to the power card, with fuel pump engaged, but with the indicator drum 90 degrees out of phase with piston stroke. This illustrates more clearly the pressure changes during fuel combustion. Fuel timing or injector faults may be detected from its shape. Light spring diagram, figure 16 on page 19 of the book. Again, similar to the power card and in phase with the engine, but taken with a light compression spring fitted to the indicator, showing pressure changes during exhaust and scavenge to an enlarged scale. It can be used to detect faults in these operations. Irregularities in diagrams. Some irregularities in the shape of an indicator diagram illustrate incorrect engine operation. If the same fault appears on diagrams from all cylinders, the cause must be a general one, such as fuel condition or supply, turbocharger system, exhaust, engine cooling, or even incorrect camshaft timing. Indicator diagrams affected by some of the more common faults are illustrated. Fuel ignition timing. Provided the fuel is at the correct temperature and the injector operating normally, the time between injection of fuel and ignition, the ignition lag, is almost constant. Consequently, ignition timing faults signify a corresponding timing fault in the injection. They will affect the shape of the power diagram, but are far more easily detected on an out-of-phase diagram. There follows figure 17, which is on page 19. Early ignition. This will cause an abnormally high peak pressure in the cylinder at about the top of the piston stroke, shown in figure 17. A heavy shock load will be transmitted to the running gear and bearings with a corresponding knocking sound. Although thermal efficiency is high and exhaust temperature reduced, the shock load and consequent vibrations may cause damage. Causes of early ignition may be incorrect fuel pump timing, broken or wrongly set injector springs, incorrect fuel condition, or overheating of parts within the cylinder. Late ignition. It can be seen from figure 18, which is on page 20 of the book, that this causes a low peak pressure which occurs well after top centre of the piston. Power is lost since the fuel is not burned correctly to transmit power at the most effective part of the stroke. Combustion may continue during the expansion stroke, see afterburning, and may be incomplete, giving loss in energy produced, high exhaust temperature, and smoke. Late ignition may be due to excessive injector spring setting, poor atomization, high viscosity or poor quality fuel, fuel pump leaking or incorrectly timed, low compression, insufficient supply of combustion air, or undercooling of parts within the cylinder. Afterburning. This refers to slow or late combustion of fuel during the expansion stroke of the piston, and shown by a rise in the expansion line during the latter part of the stroke, shown in figure 19 on page 20 of the book. Exhaust temperature and pressure will be high, with burning fuel and carbon passing to exhaust. This may burn exhaust valves and foul the exhaust system, with risk of turbocharger surging or uptake fires. High temperatures within the cylinder cause a deterioration in lubrication and possible damage to liner surface and piston rings. There may also be burning of the piston crown. A leaking fuel injector can be detected by a loss in power in the affected cylinder together with smoke at exhaust and high exhaust temperature. There may also be a knock or pressure wave in the injection system. An indicator diagram taken from this cylinder will show fluctuations of pressure during the expansion process due to secondary burning of the fuel leaking from the valve. This is shown in figure 20 on page 20 of the book. A higher expansion line at the exhaust opening indicates afterburning. Loss in power will be due to incorrect combustion. Since the fuel pressure wave from the fuel pump must refill the space left by fuel leaked from the injector, this may also cause the knock. Hot gas from the cylinder may blow back into the injector tip, forming carbon and choking the atomizer. Carbon may also form on the outside of the atomizer due to burning of the dribble of fuel. The injector should be changed and tested. To reduce the possibility of leaking injectors, good maintenance of fuel pumps and injectors should be carried out with routine changing of the injectors. Fuel must be purified and filtered and must be supplied at the correct temperature. Fuel injectors must also be maintained at the correct temperature. A partly choked fuel valve may be due to contamination in the fuel, in which debris may choke the small atomizer holes in the injector. Alternatively, it may be caused by a leaky injector, allowing hot gas to blow back into the injector, causing carbon to form and choking the injector. The overheating of an injector nozzle may also cause a build-up of carbon. There will be a loss in engine power. There will probably be hammering in the fuel pipes between the fuel pump and injector, and this may lead to rupture of the fuel pipe. A choked valve can be confirmed by indicator diagram power and draw cards, shown in figure 21 on page 21 of the book, and by reduced exhaust temperature. The remedy is to change the fuel injector, clean the fuel system, and ensure correct centrifuging and filtering of fuel, and to maintain correct fuel valve temperature. Low compression. This is shown by low pressures on a compression diagram, such as in figure 22 on page 21. It is probable that first evidence was from faulty combustion. Low pressures may be due to a lack of air being supplied, from turbocharger faults, choked scavenge ports or inlet valves and so on, or by air escaping past the piston during compression, which can be due to worn or broken piston rings, worn cylinder liner and other causes. But blow-by or blow-past is usually detected during the expansion stroke. Blow-past or by is a term used when combustion gases at high temperature leak past the piston between the piston rings and cylinder liner. This will cause rapid overheating, removing lubrication, causing further damage to the surfaces and possible piston seizure. Burning gas will enter scavenge spaces in two-stroke engines, causing fouling, overheating, and even scavenge fires. In four-stroke trunk piston engines, these gases will enter the crankcase with severe risk of crankcase explosion. Blow past may be caused by excessive cylinder liner wear, lack of cylinder lubrication, worn, broken, stuck or poorly maintained piston rings, worn piston ring groove landings, allowing rings to cant and jam, carbon jamming rings in grooves, and it will be aggravated if the engine is overloaded. The remedy is to gauge the cylinder liners and renew them if necessary. Overhauling the pistons, cleaning the ring grooves and gauging them, and machining or fitting new groove inserts as necessary, as well as renewing piston rings with the correct clearances. Maintaining cylinder lubrication and avoiding overload will also prevent blow past. Exhaust valve opening. Exhaust valve opening on a slow-running engine can be checked by means of a light spring indicator diagram. This will not give an accurate timing check, but by comparison with a normal diagram or one taken during original engine trials, it may be seen if valve opening is early or late. This is shown in figure 23, which is on page 22 of the book. Early opening of exhaust valves will cause a loss in power, since pressure is released too soon. It will give a high exhaust temperature with a risk of overheating and contamination. Late opening will reduce the scavenge efficiency by reducing blowdown. It will also affect the supply of energy to the turbocharger. Choked exhaust. The pressure during valve opening does not fall as rapidly or as far as it should if the exhaust is choked. This is shown in figure 24 on page 22 of the book. It also prevents correct blowdown and the recharge of the cylinder with air. It causes a loss in power, high exhaust temperature, smoke, and a possible surge in the turbocharger. It is the result of contamination due to incorrect combustion or excessive cylinder lubricating oil. Power balancing of engines. For economy and efficient running of an engine, equal power should be produced from each cylinder. This is then said to be power balanced, and it may be necessary to make some minor adjustments to achieve this. Power produced is related to the quantity of fuel injected, and balancing is carried out by small adjustments to individual fuel pump controls. Adjustments are limited to ensure units are not overloaded, exhaust temperatures are not excessive, and that pump controls still cut off when brought to stop. Fuel pump rack positions and exhaust and cooling return temperatures from each cylinder should be noted. Equal exhaust temperatures on their own do not show an accurate balance, however, particularly in turbocharged engines. Figures do tend to follow a pattern for a given engine, and this may give some indication. Power balancing can be checked by measurement from indicator diagrams by calculating the area or mean height from each cylinder. For medium and high-speed engines, it may be impractical to use a normal engine indicator due to the high velocities of parts causing vibrations in springs or drive mechanisms. If other means are not available, power in the engine may be related to peak or maximum pressure in the cylinder. Some manufacturers recommend that the ignition jump, the difference between peak pressure and maximum compression pressure for each cylinder, may be used to check power balance. A number of assumptions have to be made regarding the operating efficiency of the engine. In order that these can be justified, it is particularly important that regular and correct maintenance is carried out on the engine and that any deviation from normal running is noted, investigated, and corrected at the earliest opportunity. Fuel injection equipment is particularly important, and fuel pump settings, clearances, and timings must be checked and maintained during periods when the engine is out of service. Fuel injectors must be changed regularly, cleaned, and tested to ensure trouble-free operation. The injector is the most likely part of the system to be subject to faults in service. A fault in one injector will cause loss of power in the affected cylinder, but may also mean that other cylinders are subjected to overloading as the engine governor attempts to maintain normal total power or speed. If an engine operates in an unbalanced condition, some bearings and running gear may become overloaded. This may cause overheating and bearing failure. Overload in cylinders may cause piston blow past, with the corresponding dangers of overheated or seized pistons. Unbalance will also set up vibrations which, if maintained for a prolonged period, will cause fatigue from the fluctuating stresses induced. This may in turn lead to fatigue cracking of metal in bearings, fracture of bearing studs or bolts, cracks in crankshaft and bedplate, and slackening or failure of holding down bolts. A watchkeeper may ascertain that running conditions are normal by observation of the relevant temperatures and pressures, particularly exhaust and cooling return temperatures, lubricating oil, and turbocharged pressures. The exhaust should be clear of smoke, and there should be no unusual noise or vibration. Peak Pressure Indicator. This instrument will measure and record the maximum pressure within a cylinder. The one shown in Figure 25, which is on page 23 of the book, is similar in principle to the engine indicator but uses a beam-type spring which is less susceptible to vibration. The indicator is attached to the indicator cock. When the cock is opened, pressure raises the indicator piston, which records maximum beam deflection on a dial pressure scale. If fuel is shut off to that cylinder, the maximum compression pressure can be recorded. Combustion monitoring. Modern measuring instruments and recording equipment make it possible to monitor all necessary pressures, speeds, temperatures, and even wear rates within an engine. By connecting a pressure-sensing transducer to the indicator cock, it is possible to record pressure in the cylinder continuously. Pressure can be plotted on an oscilloscope traced to a horizontal scale of time or corresponding crank angle. A printout of this diagram appears comparable to an accurate, constant base scale out-of-phase diagram. Other important points, such as top center position, point of fuel injection, and so on, can be superimposed. Peak and compression pressures can be seen and equated for power or balance. Combustion monitoring may be used to maintain efficient conditions when fuel of different quality is used. Model diagrams should be made for the engine during shop testing and initial trials in the ship, and these can be compared to actual traces. Chapter 3. Gas Exchange Processes. Scavenging.